Imagine trying to teach a child how to recognize a cat. You wouldn't write a long list of rules about fur texture, whiskers, and ear shape. Instead, you'd show the child many pictures of cats until they get it. In a similar way, modern robots don't follow hard-coded instructions for every tiny decision. Instead, they learn from examples. This is the magic of machine learning. This revolutionary approach lets machines develop the ability to solve tasks that once only humans could perform. Machine learning is at the heart of many advances in robotics today. It enables robots to process the overwhelming amount of sensory data from their environment and learn from it. Instead of thinking like a calculator that follows fixed steps, these robots think more like our brains, recognizing patterns and adapting their behavior based on experience. This video will explain how these processes work, why they are so mind-bending, and how they are changing our world. Welcome to Discovery's world. Now, what is machine learning? From hard-coded instructions to learning from data. In traditional programming, engineers write specific instructions for every task. For example, if you were programming a robot vacuum, you'd have to tell it exactly when to turn, how to detect obstacles, and where to go. This method works well when every possible scenario can be predicted, but the real world is full of surprises. Machine learning, ML, turns this approach on its head. Instead of telling the machine what to do in every situation, you feed it a lot of data, examples of how to do the task. The robot then learns by finding patterns in the data. Over time, it can make predictions or decisions on its own, even in situations it hasn't seen before. For instance, consider how streaming services like Netflix recommend movies. Rather than being programmed with a fixed list of recommendations, Netflix's algorithm learns from your watching habits and those of millions of other users to suggest new shows you might like. Similarly, a robot learning to pick up a cup doesn't need explicit programming for every shape and size. It learns to recognize a cup from many examples. How robots think. The role of neural networks. Mimicking the brain with artificial neural networks. One of the most powerful tools in machine learning is the artificial neural network. Inspired by the human brain, neural networks are made up of layers of interconnected neurons, small computing units, that pass signals to one another. Each connection has a weight that the network learns to adjust through training. Imagine a network as a complex web of decision points. When a robot sees an object through its camera, the image data travels through these layers. Early layers might detect simple features such as edges or colors, while later layers combine these features to recognize more complex shapes like a face or a cup. By adjusting the weights based on many examples, the network learns which features are important and can accurately identify objects in the world. This process is very similar to how our brains work. We recognize a friend's face not by matching every tiny detail, but by understanding the overall pattern of features. Neural networks allow robots to do the same. Deep learning, many layers, big impact. Deep learning is a subset of machine learning that uses neural networks with many layers, hence deep. Each additional layer allows the network to extract higher-level features from the data. For example, in a deep learning system trained on photos, early layers might detect simple textures, while deeper layers can understand the concept of cat or dog by combining those textures in meaningful ways. Deep learning has been instrumental in tasks such as image recognition, teaching a robot to distinguish a chair from a table. Speech recognition, allowing voice assistants like Siri or Alexa to understand what you're saying. Natural language processing, enabling systems like ChatGPT to generate coherent and context-aware text. These breakthroughs have transformed how robots process information, making it possible for them to interact with their environments in sophisticated ways. Three main types of machine learning. Machine learning algorithms are generally divided into three categories. Let's explore each with everyday examples. 1. Supervised learning. In supervised learning, the robot is trained with labeled data. This means every example in the training set is paired with the correct answer, the label. The goal is for the machine to learn the mapping from inputs to outputs, so that when it sees new, unlabeled data, it can predict the correct label. Example, imagine you have a basket of fruits, and you want the robot to sort apples from oranges. In supervised learning, you would first show the robot many examples of apples, labeled apple, and oranges, labeled orange. The robot learns the characteristics that define each fruit. Later, if you give it a new fruit, it can decide whether it's an apple or an orange based on the patterns it has learned. Supervised learning is used in many applications such as image classification, recognizing objects in photos, spam detection, identifying unwanted emails, voice recognition, understanding spoken commands. 2. Unsupervised learning. Unsupervised learning works with data that has no labels. The algorithm's job is to find patterns or groupings in the data by itself. Example: imagine you dump a mixed pile of toys on the floor without any labels. The robot's task is to sort them into groups based on similarity. Without being told which group is which, it might cluster together all the toys that are red or all the ones that are soft. This approach is useful when you want the robot to discover hidden structures in the data. Unsupervised learning is often used for clustering, grouping similar items together, such as customer segmentation and marketing. Anomaly detection, identifying unusual patterns that might indicate fraud or defects. 3. Reinforcement learning. Reinforcement learning (RL) is all about learning by trial and error. The robot interacts with its environment and receives feedback in the form of rewards or penalties. Over time, it learns which actions lead to positive outcomes. Example: think of a robot learning to navigate a maze. Each time it takes a correct turn, it receives a small reward. If it hits a dead end, it receives a penalty. Over many attempts, the robot figures out the best path through the maze by maximizing its rewards. Reinforcement learning is widely used for a game playing, teaching a computer to play chess or Go. Robotics, helping robots learn complex tasks like walking or manipulating objects. Autonomous vehicles, enabling self-driving cars to make decisions based on dynamic road conditions. A well-known life example is how children learn. When learning to tie shoelaces, a child might try many different methods. Some attempts fail, and they might get frustrated, a form of penalty. But with each try, they learn what works and eventually master the skill. This same process happens with reinforcement learning in robots. How do robots learn physical tasks? Imitation learning, learning by watching. One exciting method by which robots learn physical tasks is imitation learning. In this approach, a human operator controls the robot, often using a remote or special gloves, and the robot records the actions. It then learns to imitate these actions on its own. Example: consider a robot learning how to fold a shirt. Initially, a human might operate the robot's arm, showing it step by step how to grasp the shirt, lift it, and fold it neatly. After enough demonstrations, the robot develops a policy, a set of instructions, that allows it to perform the task automatically. This is similar to how children learn by mimicking the adults around them. Google's DeepMind and other research teams have developed systems, like the Aloha system, where operators use teleoperation to teach robots tasks such as sorting objects, tying shoelaces, or even playing table tennis. These demonstrations provide the robot with a rich set of data to learn from, much like a child learns by watching parents. Reinforcement learning in the real world. Reinforcement learning plays a crucial role in helping robots master tasks that involve physical interaction with the world. Because the physical environment is unpredictable and full of variables, robots need to continuously learn and adapt. Example: imagine a robot learning to pick up a fragile object, like an egg. The robot must learn exactly how much force to use. Too little, and the egg might slip. Too much, and it might break. By receiving feedback, rewards for successful picks, penalties for breaking the egg, the robot gradually refines its movements until it can handle the egg with just the right touch. This type of learning is challenging because of the curse of dimensionality. There are so many possible ways to perform an action that the robot must figure out the optimal path through a vast space of possibilities. Just as a child practices tying shoes by trying many times until they succeed, reinforcement learning algorithms use thousands of trial and error cycles to master tasks. Simulation versus real-world learning. Training robots in the physical world can be expensive and time-consuming. To overcome this, many researchers use simulation, creating digital twins of the robot and its environment. In simulation, a robot can practice thousands or even millions of times without risking damage to expensive hardware. Example: before a robot is deployed in a factory, it might practice in a simulated environment where it learns how to move objects or navigate obstacles. Once the algorithm performs well in simulation, it can be transferred to the real world. However, simulations are never perfect. Real-life environments always have some unpredictability. Therefore, researchers often combine simulation with real-world training to refine the robot's skills further. Conclusion: the mind-bending journey of machine learning in robotics. The world of machine learning has transformed how robots think and operate. No longer are robots mere automatons following fixed instructions. They are now capable of learning, adapting, and making decisions based on the vast amounts of data they process. From recognizing objects and understanding spoken commands to navigating complex environments and performing delicate tasks, machine learning is at the heart of this transformation. By mimicking the way humans learn, through observation, imitation, and trial and error, robots are gradually developing skills that were once considered uniquely human. Whether it's a self-driving car safely navigating a busy street, a robot vacuum learning the layout of your home, or an industrial robot adjusting its grip on the assembly line, the influence of machine learning is evident everywhere. This journey is not without its challenges. Moravec's paradox reminds us that the tasks we find simple can be incredibly complex for machines. The need for vast amounts of data, the difficulties of real-world training, and the ethical implications of autonomous decision-making all pose significant hurdles. Yet, with every challenge comes new innovation. If you like this video, kindly give us feedback by commenting below. Subscribe, like, and share. Thanks for watching.